All right, we are going to complete our activity in logistic growth. We gathered data to figure out how many people have heard the rumor in a given amount of time. So I'm going to fill in this chart that we have with the number of people that have heard the rumor at that given time. And I'm going to go ahead and fill in at 9 that the last person had heard the rumor. This is going to be data that models what's called a logistic growth pattern. Within this logistic growth, there is an M. M refers to the maximum carrying capacity. In our case, that's going to be the number of people or maximum number of people that can hear the rumor. So in our case here, M will equal to 28 because there are only 28 people to hear the rumor. Okay, logistic growth is based on this statement. The relative growth rate of the population is proportional to 1 minus P over M. Okay, so this is the relative growth rate. Remember this from our previous lesson. So relative growth rate is dP dt over P equals to K times 1 minus P over M. So some of you guys can choose to remember this, or if I rewrite it by multiplying P over to the other side, I have K times P times 1 minus P over M. And if I factor out the M in the denominator, I get this. So these three differential equations models logistic growth. Okay, and what we're going to do now is we are going to solve this differential equation. Okay, but we're going to use this third form down here on the bottom. So if I separate the variables, I'm going to have M over P times M minus P dP equals to K dt. So notice how I left the K on the right-hand side and moved everything else over. Now we will integrate, and the right-hand side integral is pretty easy. I'm just going to get a kt plus c. So now I really need to work on the left-hand side. Now remember, our variable is p. M is simply a constant. M is going to be our maximum carrying capacity. So really just need to only worry about the p and the m minus p part of it. Now I'm going to do what's called a little partial fraction trick to help us integrate this. So this is our problem, m over p times m minus p. I want you to look at something. What if I put into here a minus p plus p? So I'm actually going to group this separately. And then now I actually have two fractions, m minus p over p times m minus p plus p over p times m minus p dp. And I can now simplify this a little bit. I'm going to cancel out m minus p here, leaves me with a 1. Over here I'm going to cancel out the p and leave myself with a 1. So I'm still integrating, but let's see what our integrand looks like. Now the first fraction is a 1 over p. The second fraction is a 1 over m minus p. What do you get when you integrate those? That's going to give us a natural log of p minus a natural log of m minus p. Now, did you guys catch why I wrote a minus sign over here? It was a plus. It's a minus because of the chain rule with a negative in front of our p. It's an m minus p. So now this all still equals to kt plus c. I need to kind of clean this up a little bit. When I have a log minus another log, I can condense those and make it p over m minus p, and that equals to kt plus c. I'm going to multiply everything by a negative. So I'm going to have negative ln of p over m minus p. So this is going to be a negative kt, and my constant's actually going to change because it'll be negative of what it used to be. So if you want to write minus c, you could as well. Now when I have this natural log, negative of a natural log, I actually take the reciprocal of my fraction, and I have negative kt plus my constant, and I'm going to e both sides. And the e and the natural log cancel out. So I just have m minus p over p in absolute values. I'm going to rename my constant here. I'm going to call this a e to the negative kt power. I'm going to multiply p over to the other side, and I'm going to basically add the p over and factor it out, and then divide. So yes, there are lots of parts to this. So this right here is the solution to the differential equation for logistic growth. You need to know that this differential equation over here on the right-hand side has this as its solution. So it's kind of the shortcut. If you want to memorize this, that's fine, but I do suggest that you know how to get it. Now let's continue on with this activity. Using the data points we generated at t equals to 0 and t equals to 3, so that means p of 0 equals to 1, p of 3 equals to 8, we're going to use this to find a and k. And our maximum carrying capacity was 28. using our solution, P equals to m times 1 plus AE to the negative KT power, I'm going to find A and I'm going to find K. So we first start with P of 0 equals to 1. So 1 equals to 28 plus AE to the negative K times 0 power, which works out nice because e to the 0 power is 1. So we can cross multiply here. 1 plus A equals to 28. So A equals to 27. Then we're going to use our next condition, P of 3 equals to 8. So that means I know m is 28, 1 plus 27 e to the negative 3k power. 8 times 1 plus 27 e to the negative 3k power equals 28. Divide by 8 on both sides. Now I'm going to do all of this without a calculator. So if you have a calculator handy, you can go ahead and certainly calculate your k value from this. 28 over 8 is 7 over 2 minus 1. E to the negative 3k equals to 5 over 2 over 27. So we'll take the natural log of both sides. So k equals to negative ln of 5 over 54 over 3. And if you want to rewrite that, of course, you can also ln of 54 over 5 all over 3. Now, either way, this is going to be some decimal. Write this out as P equals to 28 over 1 plus 27 e to the negative, and whatever that k is, we'll plug it in here, times t power. So plugging this into the calculator, I get k is approximately 0.793. So we're going to have here negative e to the negative 0.793 t power. So now what I want you to do is enter this into your graphing calculator and find what P of 5 is. And I get 18.5. If you look on our chart, on our table, is 17, so that's pretty close. All we had were a few data points, and actually here in the beginning you can actually see the graph. This is a scatter plot of our data points. The graph of a logistic growth curve has this S shape. They call it a telltale S-curve. Okay, so let's look at a couple other things. Explain the role of the values of M and A from number 2. So let's look at M. Well, what does M represent? M represents the maximum carrying capacity. So that's the maximum number of people that can hear the rumor. That's actually also your horizontal asymptote. And A, what does that represent? Once you plug it into here, what did this A represent? 27. So let's see, suppose that at t equals to 0, there were 2 people that had heard the rumor rather than 1. Explain how this would change the logistic growth curve. Well, let's kind of look at what would happen here. If there were 2 people that had heard the rumor, so it looked something like this, then we would have 1 plus A equals to 14 and A equals to 13. So this coefficient down here is a little bit less. Now, question number 6, using your calculator and the equation from number 2, find the coordinates of the inflection point. Looking at the graph, where do you think the point of inflection is? Over here, our graph in the beginning, it seemed to be growing really, really fast. That's almost like it's exponentially growing. But then at some point, it turns concave down and starts to sort of flatten out. We have the equation for P. This is P of T. What would we need to look for? We would need to look for when P double prime equals to 0. And I'm actually going to give you a little tip here. So let me go back and let's look at our data. So the numbers were growing, 1, 2, 4, 8. And then it starts to slow down a little bit, 13, 17, and so on. Because what's happening here in the middle? It happened right in between 4 and 5. There were 28 people total. The magic number is half of this, 14. Because what happens once you hit 14? 14 people have heard the rumor, 14 people have not. So the inflection point will always occur at the halfway point. This is always going to be when P equals to 14. So you're going to look for 14 and you're going to calculate the time here. Now I'm going to continue on here with these questions. Do you see any connection? Those need to be the same. How do you think the value of K is involved? That's sort of the rate at which people are hearing the rumor and which it's spreading. So this is our last thing. A state game commission releases 40 elk in a game refuge. After 5 years, the population is 104. They believe the environment can support no more than 4,000 elk. First thing I want you to do is to write the initial value problem. Okay, so what does that mean? When I want you to write the initial value problem, this means give me the diffie-q and an initial condition. dPdt equals to kp times 1 minus p over m. Right now, I know that 4,000 is my m. So this is going to be Kp times 1 minus p over 4,000. Now I have some initial conditions that were given. We were told that at the beginning there were 40 elk. After 5 years there were 104. So we could use either one of these for our initial condition. Okay, this is our initial value problem. So the second question, I want us to solve the initial value problem. So when you are asked to solve, that means I want you to find P of t. So in this problem, since I know my equation is P equals to m over 1 plus a e to the negative kt power, I just need to work on finding a and k. So we'll use 040 to start it off. So 40 equals to m, which actually is 4,000, so I'll write that in, over 1 plus a e to the 0 power, so that's 1. So 1 plus a equals 4,000 over 40, which is 100, so a equals 99. I have that. Now I need to find k. So since I know p equals to 4,000 over 1 plus 99 e to the negative kt power, now I'm going to use my initial condition 5,104. So this is 104 for my population at time t equals to 5 equals to negative 5 k power. We can cross multiply, take the natural log of both sides, and I'll go ahead and just tell you k equals to 0.194. My solution to the differential equation is P of t equals to 4,000 over 1 plus 99 e to the negative 0.194 t power. All right, this is the solution. The initial value problem is the differential equation. What if I were to ask you when the population growing the fastest? So this is our last parting question for today. When is the population growing the fastest? Okay, so are we talking about the first derivative or the second derivative here? Okay, the population growing. When is it going the fastest? Meaning I need to maximize dPdt. So really we are looking for what? The second derivative. Second derivative is your inflection point. When's that going to happen? At half the maximum carrying capacity. So there's a really shortcut way to doing this. You know that this is going to happen when P equals to 2,000, and then find t.